Hi everyone, welcome to Astronomy 236. We're now in week 8, and now we're going to start essentially the last phase of our course, in which we spend a lot of time thinking about planets, in particular planets like the ones that we live on here, and how the materials that we've seen, how they were produced over the course of the universe, end up forming planets and what their eventual outcomes are. So I'm going to start today by talking about the solar system, the planets that we are the most familiar with and the ones that we've known about for the longest. And I'm going to start all the way at the beginning and ask the question, what is it that we see when we look up into the night sky every night? And we see a bunch of stars. And something that you'll notice if you spend enough time outdoors, and particularly if you spend a long enough time outside, is that the stars move throughout the night. The stars seem to rotate around us. And if you take these images over and over and over and you add them up together, you actually can see the stars smearing out a path in a circle all the way around, pointing up to the North Pole. So this star here in the center is the North Star Polaris. All of the other stars are rotating around it. So this is an interesting idea. Why are the stars apparently moving around us? And the first obvious answer is that the stars are on some fixed celestial sphere, which rotates around the Earth, which remains stationary. This is the idea of geocentrism. This was the most well-accepted cosmology, and an explanation for the universe in the ancient times, going all the way up until the 15th, 16th centuries. So in this situation, the Earth is stationary, and all of the stars orbit around the Earth, or on a fixed sphere that move around the Earth. But there are some challenges to this idea as well. And in particular, some of these challenges are what we call wandering stars. So what I'm showing here are images of the same part of the sky every night. And I've circled here a bunch of stars. And some of them are staying fixed, stationary. This star isn't moving night to night. This one's not moving. This one's not moving, etc. But two of them in this image do seem to be moving. So as nights go on, they start out inside of these circles, and now it's moved all the way over here. This is what the Greeks called wanderers, planetae. And as you might have surmised from the name, these eventually became the planets that we know about in our own solar system. So, how can we describe the motion of these planets in the same geocentric system? It's a lot harder because instead of just rotating on the celestial sphere, the planets are moving much more than that. You can get some idea though, and this is kind of the basic idea of how it is. So, in this diagram, here's the Earth in the center, and then the planets are closer to the Earth than the stars, which are essentially infinitely far away in this model. And the planets are moving around the Earth as well. But instead of moving around the Earth like the stars do, which would not make them wander, sometimes these planets move around in little circles on top of their motion around the Earth. This is called epicycle theory. So by creating these spirals, these spirographs, you can replicate the motion that planets make when they wander through the night sky, lacking essentially any seeming pattern. But eventually, there was a simpler explanation for the motion of the planets, and this was what led to the Copernican revolution. The idea that instead of the heavens all revolving around the Earth and other planets revolve around the sun, which is a star like all of the other stars that we see in the night sky. In this situation, of course, the Earth is not rotating. In fact, the Earth is, in this situation, of course, the Earth is rotating. The stars are not rotating. And in fact, the Earth is moving, and you can see that the stars are remaining stationary. So this is kind of a fun way to look at these images of the sky over time. Instead of showing the Earth as stationary, which it's really not, we show the stars as stationary and show the Earth rotating around it. And it also helps us explain the motions of the planets. So here's an illustration of how that can work. So in this illustration, red is Mars, blue is Earth. And we're always moving around in our orbits, and so is Mars. But we move at different rates because we have different distances we have to traverse in our orbits, and we move at different speeds because Mars is further away from the sun and therefore moves slower. And what you'll notice is that when we look towards Mars, its apparent position compared to background stars seems to change. And when you catch up to Mars, you can even get some weird shapes, like this one right here. So here's Mars traveling across the night sky from our point of view. It can loop back and then loop forward again when Earth catches up and passes it in its orbit. So you can replicate and model all of these shapes very accurately with a heliocentric model without having to rely on all of the different intricacies of the epicycles. It's a big bonus for this new heliocentric model of the universe. So when you look at all of our planets from this context, you can start to put together the architecture of the solar system. And what you'll find is that at the center of our solar system is the sun. And then there are two planets interior to Earth that orbit around the sun closer to Earth, closer to the sun than Earth does. These are Mercury and Venus. Here is the Earth. We can infer where we are based on whether or not we are interior to or exterior to the other planets, and see whether these two planets are always closer to the sun than we would not necessarily expect them to be, for example, if they were further away. So here we are third. After us comes Mars, which is the closest planet to us as outside of us. Then much further away are Jupiter, Saturn, Uranus, and Neptune. And then there are a lot of other smaller bodies that are not technically classified as planets anymore throughout here, which we'll discuss a little bit later. It's very difficult to show our solar system to scale all in one diagram. And that's because the solar system is absolutely gigantic, but the spaces in between are even more so. So here's showing the sizes of the solar system objects all to scale. So the sun is much, much bigger than any of the small planets. So this little tiny speck here is Mercury, Venus, Earth, and Mars. The sun is about 100 times larger than Earth, and it's about 10 times larger than the largest planet, Jupiter. Saturn, Uranus, and Neptune are all also comparably much smaller than the Earth. If you want to look at the actual distances between these objects, though, it becomes much more difficult. So this is to scale. So here's the sun here, this tiny dot in the middle. And these are the orbits of Mercury, Venus, Earth, and Mars. The planets themselves are so small that they're much thinner than the line itself on this diagram. So this is only the inner part of the solar system. So I'm going to show you this red box, and I'm going to zoom out and show you essentially where this red box is on the full solar system. So all of the inner system fits within here, and the outer planets orbit much, much further away. Here's Jupiter, Saturn, Uranus, and Neptune. So the scales involved, you can barely even see some of this, you barely even see the star. You can't even see it on this scale. And even the orbits of the inner system is very tiny compared to the orbits of these outer planets. So there's just a tremendous amount of space in between all of the planets in our solar system, and it's very difficult to convey this in a single diagram. In addition to all of these major planets, these large gravitationally dominant objects, there are swarms of smaller objects. So here I'm showing the population of asteroids, which are essentially leftovers of planet formation. Asteroids are smaller rocky bodies typically that orbit around in different regions of our solar system. Some of them, which are shown in these blue colors here, are called near-Earth asteroids because they orbit near the Earth. And then there's a belt, a main belt of asteroids that orbit essentially in between the orbit of Mars, which is this red circle here, and the orbit of Jupiter out here. It's suspected that this asteroid belt is actually the remnant, or perhaps the makings of a planet that never actually ended up coming together in our own solar system. And then in addition to the asteroid belt orbiting relatively close to the star near the inner planets, there's a much larger physically extent belt called the Kuiper belt, which orbits outside of all of the planets that we know of. So here's our outer system shown here to scale. This outer ring here is the orbit of Neptune. and this is the orbit of Pluto, which was the first Kuiper Belt object known, as it's now classified. And the Kuiper Belt objects kind of cluster outside and are relatively close to the plane of the inner planets. And they're relatively large. Some of them can be as large as some of the inner planets, but they're so far away from the star that their mass is not enough to necessarily clear out the rest of its vicinity, which is why these Kuiper Belt objects are currently not classified as planets compared to the smaller inner planets like Mercury, although there's still a lot of debate over whether that classification is correct. And then finally, located much further out is what we call the Oort cloud. We've never actually detected any Oort cloud objects in this orbit just because they're so far away and they're so cold and they're so faint. But we kind of think they must be there because occasionally we see objects that fall inwards towards the sun that seem like they must have come from very far away, like the outer regions of the solar system where we believe the Oort cloud to have been. And these are also kind of smaller, rocky, icy bodies. So astronomers have had a long time to look at the planets in our solar system, thousands of years, and we've really known about their relative configuration for hundreds of years, centuries. And in all of that time, we've had a lot of chances to look for patterns in the solar system and see what the architectures of these planets can tell us. So I'm going to go through a couple of the patterns that we found and use those to explain some of the things that we think we know about how planets formed. So the first pattern that you'll notice when you look at the solar system is that all of the planets seem to be orbiting in a relatively flat and orderly way. So what exactly do I mean by that? So what I'm showing here is a schematic of the solar system where you can see the orbits of the inner planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn. Here you can actually see the planets. They're much larger than they should be. So this planet's sizes are exaggerated, so you can actually see them on this diagram. What you'll notice is that all of these seem to be lying in roughly the same plane. It's almost like if you had drawn the solar system on a flat piece of paper, then all of those orbits would have been on that same sheet of paper. That doesn't necessarily have to be the case, though. Why aren't there any planets that are going like this, that are orbiting 90 degrees away from the others? And in fact, some of the more distant objects in our solar system, like Pluto, like the Kuiper Belt objects, do seem to be tilted with respect to the other planets. But the big planets, the gravitationally massive, the gravitationally dominant ones, seem to be all orbiting in this plane. They also all orbit in the same direction. So the planet moves around its orbit in a counterclockwise orbit. So this is Mercury. So does Venus. So does Earth. So does Mars. So do all of the other planets. And the kicker is that also the sun rotates in this direction as well. So, what does this tell us about how these planets must have come to be? And the answer is that probably these planets formed in a disk of material. So if you remember that everything here is moving counterclockwise, then perhaps it would not be so crazy to imagine that everything formed from a disk of material that was all spinning counterclockwise. And there was just lots and lots of gas and dust moving counterclockwise that then coagulated and solidified into planets. And that's why all of our planets seem to be flat, because they were born out of something that was flat. This theory was first postulated by Immanuel Kant in 1755. So we've had a long time to think about this, and it seems like for the most part the theory is correct. When we look at observations of other stars, we can see these disks and we can see planets forming in them. And I'll talk about that in one of our next lecture bites for this week. Another pattern that we can look at involves the sizes of the planets. So take a look at this. Is it a little bit strange that of the four major planets, the four closest ones to the star are the smallest ones and are the ones that are rocky? So Mercury is rocky, Venus is rocky, Earth is rocky, Mars is rocky. They're all mostly made out of, irons and silicates, stuff that, is hard, stuff that is heavy, and stuff that is solid at room temperatures. But the outer planets are much bigger. They have much more mass. Jupiter, in particular, is 300 times as massive as the Earth, and the other planets are considerably more massive than the Earth. They also have a lot of gas, so they have accumulated a bunch of hydrogen and helium gas. Why is it the case that the inner planets seem to be different from the outer planets? The idea here is that perhaps there was something different about the disk in which these inner planets formed than the ones that the outer planets formed in. And this will be the subject of another one of our lecture bites this week. But I'll give you a hint to start off, and it involves the temperature of the disk. So closer into the star, the disk is warm. The disk is in fact so warm that materials like water can't exist in solid form. There must be in water vapor or steam. But if you get far enough away, water out here is in ice or snow. And the transition line, the transition region, is what we call a snow line. This can essentially is the snow line here. So outside of this blue circle, everything, all of the water is in the form of ice or snow. And inside of this circle, it's all in steam. And this difference is what makes it difficult to form giant planets with lots and lots of mass close to a star, but easier to do so further away.